Hello, I am Dr. Rashid Ahmed from the Department of Physics of Guwahati University of Science and Technology in the subject of classical mechanics with the course code PHY 211. We are at the lecture number 16 and the topic is conservation theorems and symmetry properties. In any physical system, if there is a symmetry present, we know that it is related to the conservation of some observable. For example, if there is a translational symmetry present in the system, then the linear momentum of a system is conserved. Similarly, if the system is invariant under time, then energy is conserved, and so on. This relationship between the symmetry property of a system and the conservation of a corresponding physical property is established with the help of a theorem known as Noether theorem. This Noether theorem, when presented in terms of the Cartesian coordinates, it works, but when we write the system in terms of the generalized coordinates, then the simple definitions do not work. In today's lecture, we will generalize the relationship between conservation theorems and symmetry properties, and we will write the system equations in terms of generalized coordinates, and we will see that how these symmetry properties in terms of generalized coordinates are related to the generalized definitions of observables which are conserved. So we start with the solution of a Lagrange equation. In previous lectures we have developed the Lagrange formalism, and we know that how to derive the Lagrange equations. So when we have this Lagrange system of equations, we know that if they are of there are n degrees of freedom, then we will have n second order differential equations, because for each degree we will have one equation. So each degree of freedom, we will have to write one coordinate for each degree of freedom, and for one coordinate then we will have a differential equation which is of second order. Now in order to obtain the solution of this second order differential equation, we have to integrate them, and since it is a second order, we have to integrate it twice. So therefore we will get two integration constants. Now we will have to determine the value of these integration constants excuse me, and the value of this integration constant is determined with the help of initial conditions. That means we will have to know the value of a coordinate and velocities and momentum, whatever the coordinates we are using, because we are working in generalized coordinates, when t was equal to 0. So the values of q's and q dots or p's will have to be known when t was equal to 0. This is called initial conditions. So assume that we determine the values of these integration constants, and solution will be completed with the help of these two integrations and with the initial conditions giving us the values of integration constants. But the problem is that this procedure does not work all the times, and there are systems which are not integrable. By this we mean that these differential equations cannot be integrated by any means. And if this is so, then we are left with a problem that we cannot know the solution. So although we are not able to know the solution or to solve the system, but still there is a way to know or to get some useful information about this system. And physicists have developed this procedure to get the useful information about the system, although it is not solvable or not integrable. And we use these symmetry properties about which are present in the system as a tool to get out this information. Now the main message which we will be developing in this lecture is that if there is a symmetry present in the system and it is still not integrable, if it is not integrable, the system is not integrable, and there is a symmetry present, so we can use this symmetry as a tool to get a useful information. But using a tool to get anything, we have to know that what we want to achieve with the help of this tool. So the achievement is to know the conserved quantity, and Noether theorems actually guarantees the derivation of this conserved quantity. So in today's lecture, what we are going to do is to look at the systems which are not integrable, and then look at the symmetries present in these systems, and then use these symmetries to know about some kind of conservation of some physical property quantity which is there. So this is the main message, and the rest of it is the procedure which we will develop in order to implement this method. Okay, so the procedure is that what we do is to integrate at least once, and we call it the first integral of motion, and to put the differential equation into this form. That is, it is a function of some coordinates and velocities and time, and is equal to constant. We call it the first integral of motion. And once we do this, the next thing is to get the physical information about the system, this system about of which we know the first integral of motion. And this physical information includes the conservation laws. So again, this line of connection is, the line of action is that we know the first integral of motion. Okay, now we know that we cannot integrate it further because it is not integrable, but we want to get out some useful information, some physical information, and this physical information may be some conservation law. So even without solving a system, we know that something is conserved there, and probably sometimes this information is more important than the actual solution. So how this procedure is implemented, we will understand this with the help of a very simple example. So think of a system of particles under the influence of forces derived from potential. A simple example, our illustration of this example would be a particle falling under the gravity. So if any particle falling under the gravity, so gravity is derived is a force which can be derived from the potential, and that particle, let's say some projectile, is that system. And for that system, we can have the Lagrangian, which is by definition is equal to t minus v. So we have the Lagrangian t minus v. So we know that the this del L by del x dot is used in the Lagrange equation. So why not to derive this del L by del x dot? And this del L by del x dot, you will see in a moment when I complete this calculation, will give us the definition of momentum. So that's why I want to use this calculation. So I know that the L by definition is equal to t minus v, and if I put this L equal to this in here, I will get the right hand side, that is del t by del x dot minus del v by del x dot. So let's take another simplification and assume that this v is not a function of velocity, that is x dot. Over here I am only using one component of the velocity for the simplification. Extension to the other components is straightforward. So if I assume that this potential, this v is potential in over here, is not function of velocities, then this term will go away. This is equal to 0. And with this further simplification, I am reduced to del t by del x dot only is equal to del L by del x dot. And if I put explicitly the definition of kinetic energy, since this t is a kinetic energy and v is the potential energy, if I explicitly put in here the definition of kinetic energy, which is equal to half m v square, and v square is actually x dot, this dot is the derivative of x with respect to time, giving me the definition of velocity. So x component of velocity, y component of velocity, and z component of velocity, and this is equal to the kinetic energy. So if I implement the derivative, this differential operator in here, what I get, this very simple calculation, you know by the power rule that you can differentiate this 2 will cancel out 2, and I will be left with mx dot So this means that the del t by del x dot is equal to mx dot, which is by definition is equal to momentum. So you have seen that in Cartesian coordinates, the del L by del x dot is equal to the definition of momentum. So now this information, this simple calculation which we have done, we will use it to extend this definition of momentum to the generalized coordinates, which are not restricted only to the Cartesian coordinates, which by definition are of dimension of length. So we can generalize this, and we can have the coordinates which are not necessarily of dimension of length. Okay, so let's move there and let's do that and get the definition of generalized momentum. So we call it a canonical or conjugate momentum, because if you remember, in Cartesian coordinate, if the we use the Cartesian coordinate which are of the dimension of length, for example x, y, z, these are the of dimension. For example, over here, if this is x, this is y, and this is z, then these are of the dimension of length. So their corresponding momentum, for example px, py, and pz, are of the dimension of linear momentum. But if I say that my Cartesian coordinate, I am not using the Cartesian coordinates, but I am using the generalized coordinates. For example, x could be velocity, or x could be momentum, or x could be angle, then certainly its corresponding momentum will not be of the dimension of a momentum, and it could be anything. Therefore, we use the word canonical or conjugate momentum rather than simple momentum. We say that it's a conjugate momentum, that since it is derived with the illustration of a Cartesian coordinates, where it was by definition of the dimension of momentum, so we keep the word momentum, but we add conjugate to it to know or to mean that it necessarily not of the dimension of a momentum, because the coordinates are not of a dimension of a length. Okay, so certainly this generalized momentum P of any particle will be equal to del L by del Q dot, where Q is a generalized coordinate, which means that Q could be angle, Q could be velocity, Q could be length, whatever, and therefore its derivative with respect to time certainly would be something of which are possibly not of the dimension of velocity. Therefore this P is possibly it could be of not the dimension of momentum. But this is the general definition, and you can reduce it to the Cartesian coordinates, and then you will you can reduce it to the usual definitions. Okay, so now since we know that the definition of the generalized momentum, we can make one more generalization. This was the first generalization. So mind you, there are two generalizations we are using here. The first generalization, that we are going from Cartesian coordinates to the generalized coordinates, and the second generalization, we are going from velocity independent potentials to the velocity dependent potentials. And if we implement this, the Lagrangian, in the presence of, this is a prime example of the velocity dependent potentials, when there is an electromagnetic field present, then how the Lagrangian of a system looks like. This is the shape of a system of that same particle or simple particle, let's say a projectile in a gravity, whose Lagrangian would be looking like this when the electromagnetic field is present. So in practical purposes, you can think of an electron, for example, which is moving around the proton in hydrogen atom, but since there is an electromagnetic field, then we have to add these two extra terms over here. You can see that this is the scalar potential phi, and this is the vector potential A. This gives rise to the electric field, and this gives rise to the magnetic field. So together they are electromagnetic fields, and electromagnetic fields are velocity dependent. You can see there is r dot coming in. So we have written this into three dimensions, and in terms of the Cartesian coordinates, I have dropped the first generalization of the generalized coordinates over here, just to illustrate that what happens when we go to the velocity dependent potentials. But then we will use both of these generalizations, that is to the generalized coordinates and to the velocity dependent potentials together, to develop the definition of the generalized momentum and generalized force and the conservation theorems there. So, coming back to this point, that if we have a Lagrangian of some system, think of as hydrogens, and there is an electron, and we write a Lagrangian for it in the presence of electromagnetic field. Since it's in hydrogen atom, then proton is developing an electromagnetic interaction with the electron. There is an electromagnetic field of proton. So what happens that if we want to calculate now the generalized momentum, you already know that del L by del X dot or del L by del R dot, if you want 3 dimensions, excuse me, then del L by del X dot or del L by del R dot will give you the definition of momentum. So why not to calculate it? But to calculate the generalized momentum, conjugate to the position X only. You can do it to the Y or to the Z, but only the procedure, for the illustration of procedure, we need only a 1 dimension. And if you do this, what you get here, it's very interesting. If you are understanding it, you will be shocked to know that, oh, this momentum P del L by del X dot I am getting here is not only the usual mx dot, that is momentum by the definition is mass of the particle multiplied by its velocity, and this is the first term, and we see that there is a second term coming in. So which means that it's not the usual definition of a momentum. That means that it's not the only mx dot. There is something else which is adding up over here because of the use of velocity dependent potential. So the momentum, as you see now, is a kind of generalized momentum. It's not the usual linear momentum. There is an extra term here. So the first question is whether this momentum is conserved or not. If this P, which is a generalized momentum now, is it conserved or not? And this is what we want to check now, that if this generalized momentum is really conserved quantity. Okay, so in order to do this, we have to recall, because we have already done this, a cyclic coordinate business. I want to recall to you, so that you remember it in few sentences, that cyclic or ignorable coordinate is a coordinate which is not present in the equation of motion, and since it is not present in there, it is called cyclic. The interesting thing is that if a coordinate is not present in the equation of motion, in the Lagrangian, if it is not present in the Lagrangian, what I wanted to say, it is not present in the Lagrangian, that what happens, that the corresponding momentum is conserved. That's the Noether theorem actually, that if you don't have a coordinate present in the Lagrangian, then its corresponding momentum will be absent there. Let's have a look at this thing. So the Lagrangian equation of motion would be like this. This is the so I have already written down to you the Lagrangian equation of motion. Because you can derive this. We have derived this into the previous lectures, where we wrote the Lagrangian, and from the variational principle, doing all these variations and calculation, we arrived at this thing, that is d by dt is equal to del L by del Q dot minus del L by del Q is equal to 0. And this is the Lagrangian equation, and it reduces to this d by dt del L by del Q dot, because the second term is equal to 0. Because why? You can now know this, that this L is this Q is not present in L because it's cyclic. So if this Q is a cyclic coordinate, this Q, which could be any coordinate, is a cyclic, which means, by cyclic I mean that it is not present in L, and if it is not present in L, then del L by del Q is equal to 0, and it is equal to 0, that we are left with this first term. And since we know that that's del L by del Q dot is equal to P, so dP by dt is equal to 0, and you remember that if the derivative of anything is equal to 0, that thing is must be constant, so P is constant. So to summarize about the cyclic coordinate, is that if any coordinate is not present in the Lagrangian, then the corresponding canonical or conjugate momentum is constant, that is, it is conserved. This is somehow the statement of Noether theorem as well. So this was something we have already done. We want to generalize it. and generalize it to the generalized coordinates and to the definition of generalized momentum, and see if the generalized momentum is really conserved or not. Okay, so now we go to the conservation theorem and see that the generalized momentum conjugate to the cyclic coordinate is conserved. So when okay, so you will be asking a question that when this really happens, that some coordinate is not present in the Lagrangian, then it is it is cyclic. It happens when there are constraints, because if there is a constraint in the system, then all the coordinates are not independent, they depend upon each other, and some coordinates are then cyclic, they because particle or system does not move in that direction. So when constraints are present, conservation theorem is then not obeyed. Because why? Because there are constraints, the coordinates are not independent. Remember that when we go to the generalized coordinates, we ensure the use of generalized coordinates ensure that all the coordinates are independent. There are no constraints present. This is one of the reasons we go to the generalized coordinates, that we want to avoid constraints, or it's one of the methods to solve the constraints is to go to the generalized coordinates. But the problem is, when constraints are present, conservation theorem is not obeyed. And let me explain it with the help of example. In case of a hoop rolling without slipping, theta is absent. Theta is a coordinate which is absent in the Lagrangian. You can see from over here that L is equal to t minus v for this system. I will also explain this schematically. And mx dot square by 2 mr theta dot square by 2. This is the Lagrangian actually for this system. And you can see that theta is nowhere here. Theta is not in the first term. There is a theta dot, but it is not theta. It's theta dot, it's not theta. So theta is absent in second term as well. And as well as in third term, there is no theta. So theta is cyclic because there is no motion along theta. But theta is present in the constraints equation. You can see there is a constraint in the hoop. I will show schematically that that there is a constraint. And you also know that r d theta is equal to dx. That is the dx is the distance traveled, or change in the distance, which is related to the r d theta. So whenever theta is changing, because it's a hoop rolling down, and whenever theta is changing, it is related to the multiplied by radius. It is related to the linear distance it is traveling. So although there is no theta present in the Lagrangian, it is present in the equation. This is the constraint actually, that r d theta is equal to dx. This is a constraint, and it is present in the equation of constraint. And as a result, angular momentum is not conserved, and because p theta is equal to mr square theta dot, and it is not conserved here because theta dot theta is present in the equation of constraint, and Noether theorem cannot be applied here. Okay, so what we can do then is to generalize, go to the generalized coordinate and see which thing is conserved now, because also in electromagnetic field present there, or electromagnetic field is there in a system, then we see that the law of action reaction is there, and some conserved quantities are not conserved there. So which thing is conserved then? So we say that it's the generalized momentum which is conserved. It's not the really linear momentum or angular momentum which is conserved. It is the generalized momentum which is conserved. And that's the topic of this lecture, that we are looking at some generalized quantities which are conserved rather than simple quantities which are not conserved because of the presence of some constraints, or because of the presence of electromagnetic fields, or the velocity dependent potentials. These things are not conserved, but their generalized versions are actually conserved. So the simplified Lagrange equation in this case will be equal to, as you can see, d by dt is del t by del q dot is equal to, by definition, p dot j is equal to, since this is equal to the differential of a v with respect to q, and this q, capital Q, is we call a generalized force. So generalized coordinate q is absent in this case, and what we get is the generalized force. So this q is now called the generalized force, and this F is a usual force, but this Q is a generalized force. And we will see that we will have a generalized momentum and generalized angular momentum as well, and these will be conserved rather than the simple quantities because of these constraints present into the system. Okay, so next thing is to show to you this schematically. This thing over here, you can see that if I have a system where I have a position vector r, which is depending on q, and then there is a small change going from q to dq, and r is dependent on these generalized coordinates, and this is equal to dq. This I have shown you just to tell you that this del r by del q dot is this generalized force. Actually, there are two statements in this generalized force. One is that this generalized force is a component along the direction of this F, and also the corresponding generalized momentum or linear momentum or angular momentum are conserved. So first of all, you schematically see that this R and function of q and r function of q and dq are related to each other, and their difference is dq. So by the definition of derivative, you know that the definition of derivative is del r by del q dot, that in the limit when dq tends to 0, as we have seen in the previous schematic diagram, that r minus the rq plus dq minus the r divided by dq is equal to, this is the derivative, and this is the unit vector over here, but this cancels out, and we see that this derivative is the unit vector. So by this we see that this F is actually this Q is actually the component of a force in the direction of that force. So this is the one component we are getting. So we call it a generalized force, but this is n dot F. So that coordinate, that cyclic coordinate in which we are moving, that coordinate which we have, this capital Q, which we call a generalized force, is actually a component in that direction of this actual force. And similarly, we can do this for the linear momentum. So in case of the linear momentum, we know that this is the kinetic energy, you know very well, that is the definition of kinetic energy, and the conjugate momentum would be, you can simply recall these things, that del t by del q dot is equal to mr dot and del r dot by del q dot, and we can show that this conjugate momentum is again, will be the conserved quantity, and it is the generalized momentum, generalized linear momentum. So simple manipulations, you can write this mr dot del r by del q dot equal to mv and del r by del q dot. There is a simple shifting of or removing of the time derivative. If you write all the time derivative explicitly, you will see that this will give you this definition. Just they cancel out. Okay, so this P is now the linear momentum. This generalized momentum P is now the linear momentum in the direction of n. So we have now derived two very important things. That first is the generalized force, which is the component of a actual force in direction of n, and the generalized momentum, which is the component of a momentum, linear momentum in direction of n. Then the conservation theorem says that the del v by del q, by which is definition q, that is generalized force, is equal to 0. And we can also now show that in case of the rotational motion. So we have seen that in case of the linear motion on these slides, in case of the linear motion, if we have the generalized force, that is the component of a force along the direction of the coordinate in which we are making a motion, then the generalized momentum is conserved, and that is the component of a linear momentum in the direction of that coordinate in which some small incremental distance or change has been done. Just to recall you this, repeat to you this important thing in case you have not got it. So what we are saying, that this is the generalized force, and from this schematic you see that in any any q, any generalized coordinate where we make an incremental change in that direction, the generalized linear momentum is conserved, and there is a generalized force which is in the direction of that change. Okay, that's what it meant, and we have derived that this q is equal to n dot f, and p, actually this generalized momentum is, as you have seen here, is equal to n dot this linear momentum. So this was the first example where we have seen, although the usual quantities, linear momentum and the force, were not conserved, but their generalized versions were. And we can extend this whole mechanism to the case of the rotational motion. As you know that if there is a rotational motion, then the force will be replaced with a torque, and the linear momentum will be replaced with the angular momentum. So let's see how this happens. So now the generalized force would mean to us the component of a torque in that direction. And if you do this calculation, you see that this is the del r, this is the del r, that is the magnitude of the change in any coordinate, and this is its derivative with respect to, we are just talking about the magnitude, and these are the magnitudes of the derivative. And so if we calculate the magnitude of these derivatives, and this is just the differential and this is the derivative, and then just to show you schematically this whole procedure, that we have this r, and this is the theta it is making with the, let's say, y-axis, and then we have r q and dq, and if there is a rotational motion, and this is the component of this is the direction in which we are making an incremental change, and there is an dq related to it. So this is the n in which direction we have the generalized force and the angular momentum that are conserved quantities. So we know that in the vector form, that then del r by del q would be n cross r, because we are moving in a circle, or we are somehow rotating a system, and then the generalized force would be now actually the torque, as you have seen over here. The same procedure if we repeat, which we have done in the linear case, that is f dot n cross r, or the simple, just very simple arithmetics tells you that this q is now the component of a torque. This n is a torque, you know. Now this is the component of a torque. So previously we have seen in the case of the linear motion that it was the component of a force, and now it is a component of a torque, and the corresponding conservation for the momentum would be the component of an angular momentum. If you now calculate p, which is by definition del t by del q dot, but you will see that it is the component of an angular momentum. So this is very nice, two examples where you see that if we move to the generalized coordinates, so we are doing the same thing, but since we are in terms of generalized coordinates, so these generalized coordinates and generalized momentum or generalized forces are by dimensionally are not really the forces. These can be anything. For example, in first case, in the linear case, you have seen it was the component of a force and the linear momentum, but then it became in case of rotational motion, it became the component of a torque and the component of a angular momentum, which were the conserved quantities. So what we say, that even then the usual linear momentum or angular momentum are not conserved, but their generalized versions are conserved if there is a symmetry. Although the system is not integrable, system cannot be exactly solved, but still with the help of this procedure we get an important information about the conservation properties or conservation quantities inside this system. And lastly, there is a very important conservation property or quantity, that is the energy. That energy is also a conserved quantity, and we see that with the similar procedure we can also derive equation for the conservation of energy. So consider a general Lagrangian. Again, this is a very general Lagrangian L, and this is a chain rule I have used, and this last term comes from the explicit dependence of L on time, and from the Lagrangian equation, that is del L by del Q, this is the Lagrangian equation, we And with a simple manipulation of with the help of this Lagrangian equation, we can transform this Lagrangian into this form. And if you do very simple calculation, you will come to here that this d by dt q dot del L by del q dot minus L, and this explicit because of the explicit dependence of L on time, we will get del L by del t is equal to 0. Or we can write this whole thing in terms of the first integral. Sometimes it's also called a Jacobi integral when we are talking about the energy functional. That this is the first integral of the motion, and here this dH by dt minus del L by del t, and this H can be now energy. And I leave it to you as an exercise where you prove that if this is actually a generalized version of energy conservation, but this H can be proven to be the total energy of a system when we go to the usual procedure. But anyhow, we have seen that although that there are systems which are not integrable, we cannot solve them, we cannot find their solutions, but still we can use the symmetry as a tool to find to know the information about the conserved quantities. And sometimes these conserved quantities, when there are velocity dependent potentials or there are electromagnetic fields present in the system, are not simply conserved, but their generalized versions are conserved. Then we have derived this procedure and taken two examples of the linear momentum and the angular momentum, and we have seen that these generalized quantities represent the component of a force in the coordinate in which you make any incremental change, or they could also represent the component of a torque, and similarly the linear momentum and angular momentum. And lastly, we have also seen that the energy can also be generalized, and first integral of motion can be written, and then we can see that the energy is the generalized form of this generalized version of the conservation of energy is also holds. With this, I thank you all.